we finished one antiderivative. It was a u sub and then turned into a natural log antiderivative. There are some integrals we did of trig functions. We did integral of sine, integral of cosine, or antiderivative of sine, antiderivative of cosine. So we did those already. There's 4 other trig functions we didn't even attempt. So we're going to do the 4 other antiderivatives, or the 4 other trig functions antiderivatives. And we'll start with tangent. So we're going to integrate tan x dx. So we learned u substitution. So let's try u substitution before we do anything else. What's the only reasonable choice for u here? You can't say x, so the only other choice is tangent x. There's nothing else going on in this problem, so there's no other reasonable choices. Now what's the derivative of tangent x? So all the trig derivatives probably should go on your cheat sheet. Secant squared is your tangent derivative. All right, do you see a secant squared anywhere in the integral?
No.
Nope, so it's not going to work at all. So this is out. So the only actual trick, calculus trick we knew didn't work. So what happens if your calculus tools are ineffective?
Algebra.
Go algebra / trigonometry. So how can I just use algebra or trig and rewrite tangent as something else? Oh, there we go. Sin x over cos x. Now we're going to try u sub. So let's try, we'll go with sin x. U equals sin x du equals cos x dx. What is wrong with the cos x in our original integral versus the one that we just wrote down?
Cos x is on the bottom.
Yeah, it's in the denominator. I need it in the numerator. So what's a better choice than sin x?
Cosine x.
So we'll try cos x. Du, derivative of cos x is negative sin x dx. I do see sin x dx in the denominator. The only problem is there's no negative. So we'll get the negative to the other side. Negative du equals sin x dx. Now I can take out sin x dx and write negative du. Or negative 1 du, and then cos x was u. So we got a negative 1 over u du. Move the negative sign out front. What is this antiderivative? Antiderivative of u to the negative first. What's the name of the section that we're in? Natural log. So it is natural log of u. So this is the only power that you can't do the anti-power rule to. You add 1 to the negative first power, you get 0. So antiderivative is definitely not constant. So that is out. So this is negative ln u. And u is something we made up. It should be cos x. If you want to be fully correct, there's absolute value right around there. Oh, there's something I also forgot. Plus c. We didn't have endpoints, so you get a plus c. And that needs to appear as soon as you take the antiderivative. So we get a plus c on that step and a plus c on that step.
Is there any way to remember the plus c? Just because it's sometimes hard to remember to add that plus c. Just remember to do it.
Yeah, when you take an antiderivative, you're either going to plug in endpoints or have a plus c. One of those two is going to happen every time you actually integrate. And the step I integrated was between this and this. That was where I actually integrated. So when that antiderivative, the integral sign disappears, so when this thing actually disappears, that's when you either go plus c or think about subtracting endpoints. So we'll do cotangent next. Oh, let's summarize this. So we had the integral tan x dx equals ln cos x plus c. And I'm going to switch into u's because that will make your brain think of u substitutions. So we're going to replace all these x's by u's. So tan u du, antiderivative is negative ln absolute value cos u plus c. These antiderivatives are hard to remember in my opinion. So I would probably write them on my cheat sheet, at least at this part of this point in the quarter. For completeness, I'll also write the sine x dx and cos x dx. I'm going to guess and check. Oh, let's write them with u's. So the antiderivative of sine, I'm going to guess is cos u plus c, and I'll guess this one as sine u plus c. One of these I know should be negative. The derivative of cosine is negative sine. So that means cosine needs a negative sign in front. So these are from pre-calc or from Calc 1 right here that we did these two.
So any integral that is not a c, that does not have a c in the name, has a negative in its derivative.
His name that I would just remember the way I do it. I just remember derivative of cosine is negative sine, and derivative of sine is regular cosine. So I tend to not memorize antiderivatives. So if I was taking this test, the midterm in here without, or just taking it as a student, I would write the antiderivatives that I can't remember down. I can remember sine and cosine antiderivatives. And if I forget, I can just rewrite them down, guess, and check like I just did, and have them in 10 seconds or so. So we'll compute antiderivative of cotangent. So this is going to work out almost exactly the same. So we're going to do the same first step, write it as cosine and sine. This one is cos. Oh, why did I go use? I want x's. Cos x dx. Cos x over sine x. What u sub should I use here?
Sine x.
All right. Why is sine better than cosine?
Because sine x.
Because the du will be cos and you want it as the numerator.
Yeah, I want the derivative to be a product, not a quotient. I want it to be a numerator, not a denominator. So I'm going sine x. So I want you to finish off this, get du, and go ahead and complete substitution, anti-differentiate, and then unsubstitute. So same steps we just did, they're almost exactly the same. I'll scroll up a little more so you can see everything we did. So you pretty much get the same thing except sine instead of cosine, and you didn't have a negative sign creep in. So there's no negative sign on this. So writing it out with u's, integral cotangent u du. Thanks. Integral cotangent u du is ln sine u plus c. So next up, we're going to do secant. So we'll do the same first step, writing sines and cosines. In this case, 1 over cos is all we get. So we could try the u sub again. So if I let u equal, there's only one choice, cos x du negative sine x dx. But there's no negative sine x. So that's not going to work out. So it turns out that this is actually not the route to go. And there's no way to really know that right off the bat. What we're going to do instead is multiply by something that will look very arbitrary. Secant x plus tangent x. There is no reason why you should think that this would be a reasonable thing to do. Now we're going to pick a u sub. There's two obvious choices. Either secant x or secant plus tangent. Those are the two reasonable choices to make here. Let's go, we'll go secant first, and then we'll go secant plus tangent if that doesn't work out. So derivative of secant, anybody know derivative of secant?
Secant tangent.
Secant tangent. Now we don't really have a secant tangent unless we distribute secant to the numerator. And then I'll see a secant squared plus secant tangent. So let's go ahead and do that distribution. This is just algebra. So the du I just saw was basically that part right there that I circled. But unfortunately, there's addition happening. So I can't just make that substitution. If that was multiplication, it'd be a different story. Let's try the other u now. So I know derivative of secant is secant tangent. What is the derivative of tangent? Secant squared. So I got secant tangent plus secant squared. Now, I see secant squared plus secant tangent dx. And now it will work out perfectly. I see the full right there, du in the numerator. So that whole thing turns into du, and you got 1 over u. And we'll now take natural, this is a natural log antiderivative. We get a plus c because there's no endpoints. And finally, we unsubstitute. And we get natural log of secant plus tangent. And we'll write this with u's. So I'm going to summarize this with u's. How can you check this?
Take a derivative.
Take derivative. You got some serious chain rule. But the good news is we already know the derivative of secant plus tangent. We computed that already. So a lot of times when you check, you'll have done half the work already somewhere in your u sub. You'll have already done that derivative. So that is our secant, and last one, cosecant. So we'll do the same first step. Well, we got to figure out what in the world we're going to multiply it by. So let's try to come up with this on our own. Who remembers the derivative of cosecant? So you should be bringing your cheat sheet. Yep, cosecant, negative cosecant, cotangent. So there's a few reasons I ask you what these derivatives are. One of the main ones is so you realize you don't know them. So if you don't know them, then you need to have them on your cheat sheet. So these are things I'm asking you because they're facts you should know. And if you don't know, that's what your cheat sheet's for, because there's starting to be quite a few things you have to remember. So if you can't remember them, you need your cheat sheet, and try to organize it. Put your trig in one spot, natural log exponential stuff in another spot. When we learn all these crazy integration tricks, that'll go in your integration trick spot. So try to sort it so you can, oh, it's trig. It's going to be right there. All right, so I see cosecant. So part of this needs to be a cosecant cotangent. Now, what else can I try? Let's try another cosecant. So we'll pretty much do what we did last time, except instead of secant plus tangent, I'm going to go cosecant plus cotangent. So I'm going to do the co of each of those, and we'll see if it works out. So what I did is legal. I just multiplied by 1. So I didn't do any naughty math. The question is this going to work out the way that we hope it is? Yep.
Would we need a negative in that? Because there's a negative in our derivative?
Maybe. Well, yeah, we may need to do maybe a minus instead of a plus, but we'll see. Quite possibly. There certainly will be a negative somewhere. All right, so
Your cotangent and cosecant adding or multiplying?
Yeah.
Add together. So I'm trying to replicate the form we had at the top of the board, except I see that the derivative is going to be cosecant cotangent. So there's going to be a cosecant. Here's cotangent. So I'm hoping the other, so when I try u equals cotangent plus cosecant, that the other part of the derivative will be cosecant times cosecant, or cosecant squared. And we'll see if this actually works out. Hopefully it will. Well, I have the shortcut written down right here, and this is what it is. So now we're going to go u equals, we're really picking the denominator u is really what we're doing, and hoping that the numerator is the du. So we're picking the denominator to be u and hoping that du is the numerator. So derivative cotangent is negative cosecant squared. Derivative cosecant is negative cosecant cotangent. So the cosecant derivative and cotangent derivative are just like the tangent and secant, except they're negatives. And they use all the cofunctions. So I do see a cosecant. So if I distribute the numerator, we get cosecant cotangent plus cosecant cosecant, cosecant squared. So I just rearranged with algebra, distributed in the numerator there. So I see cosecant cotangent, and I see cosecant squared. I just don't see negative signs. So we'll factor out the negative sign, and then multiply by -1. So we have negative du equals cosecant squared plus cosecant cotangent dx. So we'll just bring the negative out. Luckily, they're both negative, so I didn't have to change the sign on one of them. They're both negative. So we get 1 over u. The denominator is u, dx, and the whole numerator became a negative du. Now if you don't use parentheses, it looks like you're subtracting, not multiplying by a -1. So make sure it's obvious what you're doing. So we have negative integral 1 over u du, negative ln absolute value u plus c, and then unsubstitute u is cotangent plus cosecant. And there's our final antiderivative back in x's, and we'll summarize with u's. So it's a little strange that we're doing the antiderivative of some trig functions in the natural log section. But it turns out that's the only way you can actually get these antiderivatives, because they turn into 1 over u's at some point, and then the only way to integrate that is with the natural log. So that's the end of logarithms. We're going to go to exponentials. So definition of e to the x function. Do you remember anything about e to the x and how it relates to natural log? What was the most important? Almost. So let's try to rewrite. So what you should have remembered from pre-calculus is how to flip a logarithm around to an exponential. So we move the base to the other side, and we get this relationship. Oh, let me switch x and y actually, so it matches what I have up here. So this is how logarithms and exponentials are related. What they actually are inverses of each other. So this says they're inverses of each other. If we write that down a little more carefully, e to the x, what that is natural log inverse. So it's the opposite or the inverse function. So e to the x function is ln inverse of x. So let's look at, we'll do some limits first, and then we'll look at some algebraic properties, and then calculus properties. So the only thing we know about e to the x right now is this the inverse of natural log. So I don't think I graphed the actual natural log function this quarter when I did it, the natural log yesterday. this is the natural log graph right here. We said 0. When x is 1, you get 0. So that's going to be the x-intercept at 1. And then when x is positive, you start to gain that positive. Or when x is greater than 1, you have positive area. When x is less than 1, between 0 and 1, you have negative area. So this y value corresponds to the amount of area you would have under that 1 over t graph. So here's a graph of natural log of x. The only problem is our limit is for the ln inverse function. So what in the world does that mean? So one thing we can do, we could rewrite it as natural log inverse is e to the x. You can think of e to the x function. Or we can think about the inverse. So normally natural log eats x's. In this case, natural log inverse, we could think about maybe it's better if we just invert the graph. That might be easier. So let's invert the graph. So this is what we did in pre-calculus 2 class. And we're going to take a mirror image. So x equals 0. The mirror image is y equals 0. And we just took the function and the reflected across y equals x, and we got the inverse graph. So that's how we can take a graph, get the inverse, by reflecting across y equals x. Now we can answer the question, what happens when x approaches infinity on the blue graph? So what happens when x gets really big? What happens to y? It's really big too, so it's going to approach positive infinity. And the other limit that's interesting, negative infinity. So what happens when x approaches negative infinity, or we go far to the left? Yep, we got y approaching 0 right there, our horizontal asymptote. So we're going to get 0. So there's our limits. And now we'll go into some algebraic properties. So first one is e raised to the ln of x power. So the only thing I've really told you about e so far, it's ln inverse. So e, you could think of this as being in parentheses. And then e is ln inverse function. So e is natural log inverse. What happens if you go function inverse of function of x?
The functions
They're going to cancel out. They undo each other. And this comes from f inverse f of x equals x, which is also the same as f of f inverse of x. So function inverse cancel each other out. So this algebraic property is right from the definition. E is defined to be ln inverse, so they better cancel each other out. We can do the other way. So composing in the other order, e to the x is ln inverse. And we see natural log of natural log inverse cancels out to just x. So you can compose them either order. You get back to x. So we just summarize these. So there's our first two properties. Those are right from the definition. And we're going to take derivative now of the second one. I'm going to take derivative of the right side. You're going to do derivative of the left side. So the derivative of the right side is 1. What rule do you need for the derivative of the left? You definitely need to know the derivative of natural log, but you also need a chain rule, because it's not natural log of just x, it's natural log of a function of x. So use a chain rule. And I'll give you a hint, you have no idea what the derivative of e to the x is. So you can just leave it as some fraction times derivative e to the x. You just leave it as, I don't know, derivative e to the x, so I'll just write it as derivative e to the x. So what is the first part of the derivative, the chain rule?
1 over ex.
There we go, 1 over that function, so 1 over e to the x. So all I'm going to do is solve for the derivative e to the x, like we did before. So I'm multiplying by e to the x. So 1 times e to the x, e to the x. So we just figured out is the derivative e to the x is equal to e to the x. There's only one other function I know of that is its own derivative. Any function you can think of that is its own derivative? 0. It's not very exciting, but derivative of any constant is 0. So derivative of 0 happens to be 0. But that's the only other function that I know of that is its own derivative. And that's sort of trivially its own derivative. It's not very interesting. So this function is its own derivative, and it's definitely an interesting function. All right, so that's the derivative e to the x is e to the x. So we'll do an example. Find the derivative of e raised to the cosine of x power. Not the x power, but the cosine of x power. So you have a chain rule happening here. So go ahead and take 20 seconds and see if you can write out the derivative with the chain rule. So your derivative is just the function itself, e to the cos x times the chain rule, which is derivative of cos x, and that's negative sine x. So that's all that's happening right there. So I forgot to write down the free antiderivative we get. Writing out with u's. The antiderivative of the right side is the left side. So this one's a little bit strange, but it matches up with its derivative. Antiderivative e to the u is e to the u plus c. And let's find this antiderivative. There are endpoints. So this is not just e to the x. So this is e to a function of x. There's only one trick we know about, which is u substitution. What should I choose for u?
Sine.
So we're going to go with sine. Why is sine better choice? Because derivative of sine is cosine dx. So I see that right there perfectly. So we have e to the u du, which is the easiest antiderivative. Now I'm not writing a plus c. I'm going to write a vertical bar, and I don't know the endpoints yet because I'm in u's. So I have to get back to x's. So I need to unsubstitute e to the sine x. And now because I'm in x's, I can write the x endpoints, which are 0 and pi over 2. And I'm just plugging in 0 and pi over 2 and subtracting now. And now I just need to know trig value. Sine pi over 2 is 1. Sine 0 is 0. But e to the 0 is not 0. E to the 0 is 1. So my area under that curve is e minus 1. So there's a whole bunch of exponential rules that would be really nice if they were still true here. So you probably learned the exponential rules before the log rules, normally in pre-calculus class or before, but we did log first and exponential second. So we checked some of the log rules yesterday, or 2 days, I think it was yesterday. We're going to check some of the properties of e to the x. So let's write down the ones we know about. What is e to the a times e to the b? What should this equal? E to the a plus b. So that should be very familiar. Next up, e to the a divided by e to the b. This should be e to the a minus b. So divide bases is subtracting powers. And e to the negative a equals 1 over e to the a. And last up, e to the a to the b. What do I do with the 2 powers?
A times b.
Yeah, it's a product. So it's e to the ab. So these are properties you should have seen and used quite a bit. The question is, are they actually true the way that I defined e as the natural log inverse? So they should be true, but we're going to check. We'll just check one of them. We'll do the first one. You probably don't need to write these on your cheat sheet unless you forgot your exponential rules, in which case they may need to be written on your cheat sheet. We'll do the proof of e to the a, e to the b equals e to the a plus b. Now, if you just naively start this, you might say, oh, e to the a plus b, well, that's just e to the a times e to the b. But you just assumed what you're trying to prove. So yes, it is, but that doesn't prove that it is because you said so. Or some professor or teacher said so. That doesn't work in math. So what we're going to do is look at what do these things actually mean. So I don't know that they're equal yet, so I'm going to we'll go with y1 equal e to the a, and y2 equal e to the b. So I'm just giving these different names. Now I'm going to flip them around with the definition. Actually, let's just write it with ln inverse of a, y2 equals ln inverse of b. This is the definition of what I said e to the a is, and the definition of e to the b is the inverse of the natural log. So now I can move the natural log to the other side by just doing a regular natural log. So you move the inverse function to the other side like that, and do the same thing over here. And all that I'm doing is a property of inverse functions. So hopefully you've seen this before. I know if you've taken my math classes, I've talked about moving functions to the other side as the inverse function. So that's all I'm doing. Just taking natural log inverse the other side as natural log. So why in the world am I doing this? That's a good question. We are going to, let's add up both of these two. So all I did was used these two functions, and I'm technically using the skills of elimination, but I'm not eliminating anything. I'm just adding up the two equations. So what is ln of y1 plus ln of y2? Well, ln of y1 is a, ln of y2 is b. So it equals a plus b. What properties, now I can use the properties of natural log that we did yesterday. So what property can I use on the left side? What is addition outside of ln? Property 1. So addition outside is multiplication inside. And I think we did actually prove this property, but we didn't spend the time to prove every single property, but we're going to use property 1 right here. So it turns into a product inside. And we know these are equal, so let's take ln inverse of both sides. So we're going to ln inverse this whole thing, both sides. All right, easy question. What happens on the left side? Ln inverse of ln of y1 times y2.
They cancel out.
Cancel out. So just get y1, y2. So that's the easy part. Now right side, I could leave it like this, or I could write it as e to the a plus b. Either way. What in the heck was y1 and y2? I'm looking up to where I define them. y1 is e to the a, y2 is e to the b. I'm just looking up right there, right where I defined them. So I'm going to swap out y1 and y2, e to the a, e to the b. So we just proved, basically using the definition, that, let's see, addition of powers is the same as multiplying bases when your base is e. So again, you should have known this already. The only problem is you didn't know what in the world e to the x was. So I told you a slightly different thing about what e to the x is, and it happens to have the same properties that you've been using the whole time. So you could prove the other ones in a similar way. The last one's a little more tricky, but we won't go through the proofs of those. So every exponential function doesn't have to have a base e. They can have any base, well, I should say any good base. There are lots of bad bases. So we'll talk about good bases and bad bases for a minute, but we'll go with the definition of an exponential function right now. So this is going to be with base a. We need a to be a nice base. So if we write in interval notation, nice bases are either between 0 and 1 or 1 and infinity. So a base 1 is not good for a few reasons. We'll look at that in a minute, but we'll just say for now, this is where good bases are. So here's the definition of an exponential function. A to the x is just e to the x times ln a. Which you could write as, you could change the order around. What you don't want to do is write it like this. It's ln of a that times x, not ln of the product ax. So do exponential rules still work here? So we have base a to the b plus c, a to the b, a to the c, a to the b to the c power, a to the bc, and the reciprocal power. All right, let's try the first one. So the answer is yes, they still work here, but let's just prove the first one real quickly. So I don't know if this equals a to the b, a to the c. So what we're going to do is use definition right above. So what's a to any power? That's a to the b plus c equals, just from the definition, e to the b plus c times ln of a. So x is now b plus c. And the right side, there's going to be two parts to it. So a to the b is e to the b ln a. And a to the c is e to the c ln a. So there's going to be a lot of ln a's up in the denominator, in the exponents, basically. So we'll keep going with, let's just keep working on this side right here. The good news is, what I can do now, our base is no longer a. Our base is now e. So I can use all these properties that have base e. So I'm allowed to do any of these up here. So let's think about what's happening. We'll look just inside the power here. I'm going to distribute ln a to the b and the c. So I'm going to just distribute up in the power. So b times ln a plus c times ln a. And now e raised to a power plus another power is product. So this is e to the b ln a times e to the c ln a. And now I can use these two definitions over here. E to the b ln a is a to the b. And e to the c ln a is a to the c. So this first one is a to the b times a to the c, right there. And where we started, a to the b plus c. So this type of proof is what we call unwinding definitions. We just said, hey, this thing is defined in terms of this other thing, and we want some property. So we just basically translate it to base e, use what we know, and then translate it back. That's all we did in this proof. So why is a equals 1 is a bad base? What is 1 raised to any power? Well, I should say what's 1 raised to almost any power is itself 1. So this is a very boring function. It's a constant function, always 1. So that's why we don't use 1 as a base. The reason we don't use negative numbers as a base because you get complex values out of those very easily. So anytime you have a square root or any even root of a negative number, you get complex values. So you don't want to go negative. And 0 is a bad base too for the same reason. What is 0 raised to any power?
0.
It'll be 0. Well, I should say 0 raised to almost any power is 0. So that's also not a good base. Now when I say almost any power, we'll get into L'Hopital's rule and look at what happens when things get really strange. What's 0 to the 0 power? Because any number to the 0 power is 1, except 0 to any power is 0. So what do you get? The answer is it depends.